Magnetism is the other half of electromagnetism, which is caused by moving charges instead of static charges. Magnetic forces can also follow the type of rules that gravity and electrostatic force follow. If you have two magnetic poles, force is equal to P1, P2 over d squared. But this is not the general version of an electromagnetic force or just a magnetic force. This is a very specific type of version for a bar magnet. So a bar magnet is something that seemingly doesn't require the motion of charges in order to cause a force. If you suspend a bar magnet at its center by a piece of string, you'll have a compass. One end, called the north-seeking pole, points northward, and the opposite end, called the south-seeking pole, points southwards. More simply, these are called the north and south poles. All magnets have both a north and a south pole. Some have more than one of them. Like poles repel each other and opposite poles attract. We won't go into details about the creation of magnetic fields except to acknowledge that a magnetic field is a relativistic byproduct of the electric field. Charged particles in motion have associated with them both an electric field and a magnetic field. A magnetic field is produced by the motion of electric charge. If the motion of electric charges produces magnetism, where is this motion in a common bar magnet? The answer is in the electrons of the atoms that make up the magnet. These electrons are in constant motion. Two kinds of electron motion contribute to magnetism: electron revolution and electron spin. So electrons behave as if they revolve around the atomic nucleus and spin about their own axes like tops, but they don't actually. Spin is a quantity like charge or mass that is just a quantity that is associated with certain particles. Spin has units of angular momentum, but it is not going to be the same as an object that is literally spinning around in a circle. Electron spin is the chief contributor to magnetism. So we can see magnetic field lines actually because magnetic fields cause there to be a torque of iron particles or iron fillings, which cause them to move until they are in line with the magnetic field around them. How do you create one of these bar magnets? The trick is to find a magnet that is already magnetized, that is already strongly magnetized so that the magnetic field points from one side to the other, and you put it in that you put a piece of unmagnetized iron or an unmagnetized piece of metal that can become magnetized into that magnetic field, and that is going to cause the randomly distributed spins and the randomly distributed um, types of domains, which is what they're called, to align until they are strongly aligned in the presence of a magnetic field. So when a magnet is broken into two pieces, each piece is an equally strong magnet starting from south to north and south to north. You cannot have just a south pole or you cannot have a north pole. It is also useful at this juncture to define the right-hand rule, which is what's used for something called a cross product, where A cross B, if you have the vector A pointing forward with your finger and the vector B pointing forward with your middle finger, then the product A cross B is going to be perpendicular to both of them and in the direction that your thumb is pointing. So this is useful because the magnetic field is perpendicular to the motion of the charged particle QV cross the radius. It's not exactly that. It's also dependent on the distance between them. So a magnetic field will get weaker the farther away you are, but it is pointing in the distance of the charged particle that's moving in some direction, crossed with the radius or the distance from the charged particle to the point you're looking at, and then the magnetic field is going to be uh, pointing in the same direction as your thumb. We can look at something called electromagnets, which is a magnetic field caused by a current flowing through a wire. So if you have a wire which is carrying a current up, and then you go some distance out, then you will see that the magnetic field is going to be pointing perpendicular to both of them. And as you go out and rotate that radius around, it's going to go around in a circle. So a magnetic field caused by so the magnetic field caused by an electromagnet magnet by a current just passing through a wire is going to follow a different form of the right-hand rule, which is that if you point your thumb in the direction of the current, then the way that your fingers are curling like this is going to demonstrate the direction of the magnetic field, which, as you can see, is going to be a circle around them. However, if you have a loop of wire instead of just a wire going straight through it, and that has a current pass through it, what you are going to see is that the magnetic field is going to point straight along the distance, the center axis of the wire, especially if you have the third situation, which is called a solenoid or a coil of wires, where each wire carries a current, and that is just going to cause there to be a magnetic field pointing straight through the center of the wire. We now come to the more complete and accurate version of magnetic forces, which is that force is equal to QV cross B. So in this first diagram on the left, we have an electron beam going through a horseshoe magnet where the magnetic field is pointing from north to south. And because the electron beam has negative uh, current, because the current is pointing in the opposite direction of the beam, because the electron has a negative charge, when we point backwards and towards the left, we see that the force is going to push the electron beam up. And then if you have a current passing through a wire, depending on the direction that the current is passing through, it will either go up or down, but it will be perpendicular to both the magnetic field and the direction of current on the wire. So magnetic fields are perpendicular to the currents that cause them, but they also cause there to be fields which are perpendicular. They also cause there to be forces, rather, that are perpendicular to the fields and the forces that are acting on the moving charges. Coming to more practical uses of magnetic fields, the simplest meter to detect electric current is a magnet that's free to turn, a compass. The next simplest meter is a compass and a coil of wires. When an electric current passes through the coil, each loop produces its own effect on the needle, so a very small current can be detected. A sensitive current indicating instrument is called a galvanometer, named after Luigi Galvani, who in the 18th century discovered that dissimilar metals caused twitching in a frog's legs that he was dissecting. A galvanometer can be calibrated to measure current, amperes, in which case it is called an ammeter, or it can be calibrated to measure electric potential, volts, in which case it is called a voltmeter. You can also use a current and a magnetic field to cause there to be a motion along the object. So if you pass a current through a loop of wire and place it in a magnetic field, then the magnetic field is going to cause there to be rotation of the wire, which can be used to find mechanical or motion-based energy or to do mechanical work. To finish up, we are going to talk about the fact that the Earth itself has a magnetic field, which is why compasses are able to work the way they do. That why compasses are able to point north or south and tell you which direction you're going. So the magnetic pole in the northern hemisphere is now located about 1,800 kilometers from the geographic pole, somewhere in the Hudson Bay region of northern Canada. The other pole is located south in Australia. This means that compasses do not generally point to the true north. The discrepancy between the orientation of a compass and the true north is known as magnetic declination. Most Earth scientists think that moving charges looping around within the molten part of the Earth create the magnetic field. Some Earth scientists speculate that the electric currents are the result of convection currents, heat rising from the central core, and that such convection currents, combined with the rotational effects of Earth, produce Earth's magnetic field. Because of Earth's great size, the speed of moving charges need only be about a millimeter per second to account for the field that we see. We will also see that Earth's magnetic field is not a constant thing. It has been moving, and it does tend to flip in relatively short geological timescales. So the slight magnetism that results from can be measured with sensitive instruments as samples of rock are tested from different strata formed throughout geological time. The magnetic field of Earth for different periods can be charted. This evidence shows that there have been times when the magnetic field of Earth has diminished to zero, followed by reversal of the poles. More than 20 reversals have taken place in the past 5 million years. The most recent occurred 700,000 years ago. Prior reversals happened 870,000 and 950,000 years ago. Studies of deep sea sediments indicate that the field was virtually switched off for 10,000 to 20,000 years just over 1 million years ago. We cannot predict when the next reversal will occur because the reversal sequence is not regular, but there is a clue in recent measurements that show decrease of more than 5% of Earth's magnetic field strength in the last 100 years. If this change is maintained, we may well have another reversal within 2,000 years.